There is also another interesting number. This is, for example, numbers when when we have some interrupt to try to, which basically signaling that our system, operating system, try to overtake the control of NIC card, but it doesn't succeed. And in older drivers, we have this number, and another number here is one level of magnitude lower, which I think that it is due to polling management system. And another, last, my observation here is use dynamic polling for bandwidth partitioning and isolation without any support from switches and routers. What does it mean? It means that we don't have to have switchers, routers, everything. We just have to have one CPU, one, let's say, cluster, whatever it means, computer, where we could do it with, of course, network interface card or cards, and we can multiply that on so much levels we would like to do. This is another picture. I tried to be as much descriptive as it's possible in this picture. Just again to show you from one perspective how it works. Basically, so you have one application, thread, Solaris container, virtual machines, whatever. From one picture, we should read picture from the right to left. Maybe I should make it from the opposite side, but I make it in this way. We have, for example, some application level, whatever it means. It says threads, large containers, virtual machines, whatever. We dedicate to them certain amount of CPU power. One CPU, two CPU, multi-core processor, processors, whatever. Then everything is merged into one SQ, which is old technology. And now comes our cutting-edge technology, it is virtual NIC. This Q means Q, like Q, but I didn't have space to put it. It means kernel Qs and trees. You have a ring, RX, TX, DMA ring, and you have here a classifier. NIC, network interface cards. But basically, what's happened here, I tried to be more descriptive, but if you have a question, just ask me. This classifier here also belongs to, it says, for example, I just wrote one of examples. Classifier did this classification to other logical connections to this concrete network interface cards. But it also belongs to this, our Crossbow technology. Because all these rings, DMA rings, which each network interface card has to have, we divided this into multiply of them. And also, we need some kind of multiplexing all these stuffs. In Crossbow technology is called classifier. And of course, later it goes just to the network, to the NICs, to the real hardware, let's say. So basically, outside the network, we cannot see the Crossbow technology. Only what we can see from outside the world is just usual traffic. TCP, UDP, whatever. Virtual network containers. This is also on the beginning of my presentation. I show some also. I talk about containers and everything. And in last slide, I also talk about that, but basically it enables us to make our zone, to make container, logical domain, whatever it means, whatever we would like to do, Xen domain, for example. This is something I'm talking about when people ask me that they have a lot of stuff running on Linux. And I told them, okay, just run Xen Linux, and you'll have all your Linux applications here. And they started to talk me about overhead. And I told them, and there are some presentations from some developers who explain that this overhead is 2 or 3%. So basically, Sun's virtual logical domains, containers, zones, Xen domains give so small amount of overhead if you want to deploy some virtualization of some other operating system inside OpenSolaris. But it is another story. I will just now fix my talk on Solaris Global Zone. Zones. We have here, for example, 2 zones in our picture. And I just showing here how it behaves to the external world. We have, let's say, zone 1, zone 2, and we dedicated one virtual NIC with 100 megabits per second, and another virtual NIC 200 megabits per second. We also, as we saw so much times before, have a lot of these rings. We have these Eric Stakes DMA virtual rings, as much virtual NICs we have. And these zones communicate with clients without problem. So basically it means that if you want to deploy Sunray thin client system, you cannot have a bunch of NICs cards. You just could have, you can consolidate so much lower level, and also you can put much higher bandwidth on one place than on another. This is something which is important. Also, I would like to stress something on this slide. It's about observability. Watch real-time usage for each virtual NIC. It means that we can, this is something I really like in Solaris, we can watch our systems which are in production, in live production, and we could track them, we could observe them without interrupting their they working. So, for example, nobody will be affected by our observation, but we can take valuable data for our future development. So, it means history at no cost. We also can do SNMP and key stat per each virtual NIC. I think I showed MP stack, pardon, but we also can do it. And history, all history we can put in logs without affecting that. It means if you are in banking sector and you deployed this technology, bankers work regularly without even knowing that some system administrator just tracking how system performs. It doesn't track transactions and logging that, but just tracking utilization of whole system and putting logs. Of course, it comes later to visualization, to statistics and stuff like that, but it is very useful for development sector, which they can use those informations, which are 1, 2, 3 days old, so it's new, fresh, to see how system performs and what they need to do. Do they need to improve, how they need to adjust the IT infrastructure, basically. Do they need to consolidate, what to consolidate, how to consolidate, and stuff like that. Again, virtual machines, how they behave. They behave if you have some Solaris operating system and these guests operating systems. I just show here this. We have this NIC virtualization engine, which basically all other guest of Solaris virtualization engines just communicate with host. And other guest OS, also we can, like in this picture, divide it in a couple, or just leave it one, which is really logical, I believe. And it goes also all to hardware flow classifier to NIC later. Network machines. In this slide, I wanted to show you one, let's say, typical, not problem, typical design. We usually, companies has some resources which they would like to publish to go to the internet, and also would like to have their own intranet, well protected. And they usually do it by really dividing the hardware, by making, for example, you could see what is for outside of the net and what is for intranet. And this Crossbow technology just consolidate, put everything in one cluster, let's say. And so basically we would have a router, firewall, everything inside one cluster. It means that our cluster could work for some machines and behave like intranet, and for other machines he could behave like internet. It just depends on which virtual NIC we connected our clients. Let's say in this client-server technology. If we don't know, if we don't speak about peer-to-peer technologies. And basically, we don't need a router. Router is just inside the CPU. A router is also virtualized. Router do this job on a software level. And also, for each of these layers in this stack, we have open, of course, because all this technology is open. Everybody could see the source code, and everybody could see how project goes. Subscribe to mailing list. Later I will show you. But anyway, this technology has been designed without keeping in mind that for any of these layers, in OSI model, we have API where independent software vendors could write their own piece of code if they don't like ours or Crossbow. So it means if they are not satisfied with IP layer, for example, they could rewrite it or update it or modify it. If they don't satisfy it with how we solve virtual NICs in communicating with these virtual rings, RX takes DMA, they could write their own. Each part of the Crossbow technology is again modular structure and has really strict API which enable rapid development for independent software vendors to write their own if they're not satisfied. This is, I would like to concentrate just about the routers, because I just mentioned that you have the router in a cluster without needing exact routers. And this is just in the last slide, I just speed up my talk without explaining routers. Now I will explain this too. This is anatomy of typical router. We have a root lookup engine, usually, which is some abstraction I wrote here because we have a lot of different routers, from quite simple routers to very complex routers from other companies. I don't want to advertise any. We have routers which are quite complex, which communicate between each other using their own communication protocols to update the lookup table, and this is how internet works. And we have here just a typical router. It means we have here port, queue. Again, I wrote queue as a queue, the row serial, because it didn't have space. And we have here lookup engine, which basically has one database, lookup database, and he searched to this database, and according to this lookup engine, he put our streams to their ports. This is something quite typical. And now we change slightly to Crossbow router, which is also another type of router, but it's not, again, as I told you, it's not a real router. It's a router software design. We have here basically compute interface, which is threads, cores, compute interface. How to explain it the best? Let's say it could be threads or processes which would like to access to the network. We have here also different, I put some types of data. For example, we would like to do it by HTTPS. We would like to translate data, voice. For each of them, we have different demands regarding quality of service. And for example, for video is one, for data is another, voice is third, and also it goes to our virtual NICs. And in this Open Solaris network stack, we do by in virtual NICs the decision where our traffic will go by forwarding them to exact DMA RX Oh, okay. Now I'm near completion. This is, for example, physical network. I'm just finishing presentation. You have in a first part of the slide, how it looks. You have, for example, these all are physical hardware, basically. And on the Crossbow network in a box, you have everything in one box. It's not just a picture box, but it's for example, virtual NICs here. We could see Ether stub. This all software designed, hosts and everything into one cluster. So there is no need for redundancy of hardware. There is no need to buy a lot of routers. There is just need to buy normal amount of routers, which is used for typical cluster design. And in cluster, we can design our own network as we would like. That is just because Crossbow is a part of a larger idea called cloud. I told you that I will tell you how to administer that. There is two commands, dladm, and another I didn't put in this slide due to time constraints. Another command is netrcm. First command is data link administrator. For example, we could see here how it's created. I believe it's quite easy. DLM administrator create virtual NIC. We saw, we telling on which real NIC we would like to do and what the name of the link. Another game, we create virtual NIC tool, but now with some parameters, because in the first we are using parameters default, and here we are using some other. This -m random, it says, it talks about our MAC type. Do we want to be factory designed MAC address, or we would like random MAC address? Let's say that our Crossbow technology, Crossbow decide about MAC address, maximum bandwidth, how many CPUs we would like to use for one virtual NIC to spend, and we create virtual switch. And switch is, for example, to collect all our NICs in one, just like normal switch, and this is how it goes. And also we have another, which is NetRCM, which cares about other stuffs, for routing, for everything, but it also works on similar principle like this. So for administrators, it's quite simple. This is, if anyone want to join to our community, this is the list of places where you can find this VNM are virtual network machines, Crossbow, networking, and you have a lot of documentation really about that. And I tried to put, this is my last sentence, I tried to put all core about Crossbow technology in these 12.5 pages. That's all.